Hello, welcome to this lecture on biomathematics. Today, we will do a bunch of a set of problems. It's like a tutorial. So, we will discuss a set of problems related to what we have been learning so far. Couple of points to make things clear. I mean, the main aim of this tutorial is just like we had before. One aim is given a description. Can you write down things in mathematically? Can you think how to write down the description that you hear in terms of a mathematical quantity, and also to give you some feeling for numbers and also to train you to really solve some problems that is pretty much relevant to biology. So, let us go through the questions what we have today, and we will learn. We will try to answer one by one and discuss. And if there is anything need something is not some part of these questions, you will have to do it yourself, but I will discuss most of the answer to most part of all the questions. Okay, so let us start with the tutorial. So, it is tutorial discussion, and let us go to the first question. So, again like I will read the question in detail, and then we can go through each sentence. So, first let me read it in full. So, in mathematics we use vectors to specify direction of various quantities such as force. Imagine a cell with only 2 chromosomes. During cell division, the chromosomes are pulled apart by a pulling force generated by cytoskeletal machinery. Can you write down an expression for forces on chromosome 1 and chromosome 2 in this case? You may assume the magnitude of the force is constant. You need to specify the direction using vector notation. So, basically this is a question just to help you think using vectors. It is a very simple question, but it just you have a physical situation that you very well know, and you want to take a little step, like it's like taking a baby step. It is not a big problem. It is like taking a baby step towards writing down, thinking about the situation and writing down the force in a vectorial notation. So, it is a very simple step, but it is important that you read it, figure out how to do it, and then do it. Okay, so, let us read through this carefully. So, let us go through the sentences. So, the first sentence we say that in mathematics we use vectors to specify direction of various quantities such as force. So, this is about vectors. And now, imagine a cell with only 2 chromosomes. So, first let us just draw a picture here. So, let us draw a picture of a cell here, and let us only like draw a chromosome. So, I will draw a chromosome like this. So, this is a chromosome actually. It does not matter what the shape is, I just drew this. Okay. Now, after the cell division, so let us say you have to make these 2 chromosomes. Forget the biology of this, forget the biological detail. What we want is, we want 2 cells with this chromosomes like this, or we have to take this is what essentially happens, but for this chromosomes to reach these 2 parts of the cell. So, initially the chromosome, initially the chromosomes will be like this, and it has to be pulled apart to reach this kind of a situation, and then the cell division happens. So, you have 2 chromosomes, this has to be pulled in this direction, and this has to be pulled in this direction. So, that the chromosomes are pulled apart, and then you get this. So, this is the idea this is the kind of cell division we are thinking about. You could have 2 chromosomes becoming 4 and pulling 4 of them apart, but for simplicity let us not worry about all this. we only we only want to think about the physical part of it. So, let's look the question once more. So, during the cell division, the chromosomes are pulled apart. So, there are only 2 chromosomes and the chromosomes are pulled apart by a pulling force generated by cytoskeletal machinery. So, there is some cytoskeletal machinery to pull these chromosomes apart. So, typically it is like, typically if you imagine the situation, what you have is some cytoskeletal machinery, basically microtubules, and microtubule connected to this, and this generates a force in each direction and takes the chromosomes to both sides. So, this is what typically happens. Now, so the microtubules and the kinetochore, this structure is called kinetochore. So, they pull the chromosomes in the direction. So, what we want is, so they exert a force on the chromosomes and pull them in this direction. So, essentially what we want is chromosomes being pulled apart in that direction. So, we have this chromosomes and we want to have force in this direction. Does not matter how the force is exerted, say the details does not matter, we are not worried about it, but we want to write down. So, what do we want? Can you write down an expression for forces on chromosome 1 and chromosome 2? So, let me call this chromosome 1 and let me call this chromosome 2, and is written, you may assume that magnitude of the force is constant. That means, the force does not change with time, it is always the same force, and you need to specify the direction using vector notation. You need to specify is going in this direction and this direction vector notation. So, let us first think of direction. So, let us say this is your x axis. So, this direction along this increasing x axis, this direction is plus x and this direction is minus x. So, this is plus x and this is minus x. So, the force along this has to be proportional to some minus, it has to be some constant times minus x, and here plus x, and here it has to be minus x. So, this is clear from this. So, this is the basic idea. So, the force along this, so the force along this direction has to be plus x, and so let's think of it. So, this is F along the plus direction, or a force on the, so we call this chromosomes, we called this is 1 and this is 2. So, force on chromosome 2, which is force on this chromosome, is some F 0, which is a constant, we can assume as a constant, x cap, and F 1. So, this is a vector, force on 1 is also a vector, and this is also some F 0, but minus x cap. So, there has to be a minus sign. So, this is the, one can write F 2 and F 1 this particular simple forms, F 0 x cap and minus F 0 x cap, and assuming that the force is constant. Now, you can make the force time dependent if you want, then you can write F 1 is some F 0 function of time, but along x cap, F 2 F 0 of t x cap minus x cap. Now, you need not even have this F 0 and F 0 both. You can have this has some function. So, F 1 force on 1. So, F 0 is just notation, does not mean anything else. So, you can call this some function g of x, g of t. It can be g of x and t in principle along x cap. So, little more general, little more general, I can write f 2 is some g of x, sorry, f 2 is g of x comma t. It can depend on both position and time, and you can have it along the x cap. Similarly, f 1 can be some other function which is p of x comma t, some number p, some function p, but along the minus f. So, this can be little more general, and g can have interesting forms, and so is p. So, both f, g and p can have interesting functional forms depending on the situation. But the question here is just to give you the idea that you have to put this x cap and minus x cap, and you can actually put whatever way you want. You can say that okay, my x axis is, my cell is oriented in this particular direction and the chromosomes are being pulled in this direction. Without loss of generality, I can take this as x axis. Now, if you do not want that, you can take this as x axis and this as y axis, and you can write f, this is 1, if this is 1 and this is 2, you can write f 2 is some function of, so let us say g 1 along x cap and g 2 along y cap. So, some component in x cap and some component in y cap, but f 1 has to be just minus of, it could be, it has to be just the opposite direction. So, then you have to make sure that the direction of this is just opposite to this. So, this has to be, typically you can write this in the opposite direction. So, the direction of this is basically given by this divided by unit vector of this. So, you can write some other function, but minus of f 2 cap in the opposite direction of this f 2. So, in this way you can write it whatever way you want, but the simple way is something we discussed here, which is this is the some general case which is in a simpler, but quite general enough case. Okay. So, now this is this question on force on chromosomes. Now, let us look at the next question on diffusion and viscous drag. So, something we learned is about diffusion equation. So, one aim here is to familiarize you with some numbers also. So, let us look at the questions here. So, the questions, so some proteins do diffuse along DNA. Typical diffusion coefficient measured in some cases, typical diffusion coefficient measured in some cases is 10 power minus 12 centimeter square per second. So, this is the typical diffusion coefficient. The question is, what is the viscous drag that is being felt by the proteins? So, the question is like you have DNA and some proteins that is bound on the DNA, they can diffuse along DNA. And the diffusion coefficient which we learnt turns out approximate number is 10 power minus 12 centimeter square per second. Now, the question is, what is the viscous drag? So, we know, we have learnt the famous Einstein's relation, which said that d is k b t by 6 pi eta a. So, this part we can call viscous drag. So, you can, if you want, you can write k p t by zeta, and this is basically the viscous drag. So, whatever the bottom 6 pi eta a is viscous drag. So, we know d, we have to just calculate this, and of course, we know k, b and t. So, it is a very simple thing, just applying the formula, just applying the Einstein's relation, but given the diffusion coefficient, we can compute this quantity which is 6 pi eta a. Okay, so now let's calculate it. Let's do this, but before that, let's look at this number once more. 10 power minus 12 centimeter square per second. What is it in base pair? Because the centimeter on the DNA doesn't make any sense. The unit of DNA, typically DNA length is said or mentioned in the units of base pair. So, how do we convert? What is this diffusion coefficient if we convert that into base pair? So, let's think about it a minute. So, 1 centimeter, how do you convert? So, D we know 10 power minus 12 centimeter square per second. So, it turns out that 3 base pair is 1 nanometer. That is the rough scale. 1 base pair is basically 0.3333 nanometer actually. So, 3 base pair is 1 nanometer. So, 1 base pair is about 1 by 3 nanometer. So, now what is this implies? So, 1 nanometer actually means 10 power minus 9 meter, and 1 meter is 10 power 2 centimeter. So, this is 10 power minus 7 centimeter is basically 1 nanometer. So, 1 nanometer is 10 power minus 7 centimeter, or 3 base pair is basically 10 power minus 7 centimeter. So, in other words, 1 centimeter is 3 by 10 power minus 7 base pair, which is 3 into 10 power 7 base pair. This is 1 centimeter. 1 centimeter is about 3 into 10 power 7 base pair. So, now let us substitute this here. So, what do we get? So, instead of 1 centimeter, let us substitute 3 into 10 power 7 base pair. So, D is equal to 10 power minus 12, 3 into 10 power 7 base pair square per second. So, this is 10 power minus 12, 3 into 3 is 9, 10 power 7 into 10 power 14 base pair square per second. So, this is basically 10 power 9 into 10 power 2 base pair square per second. So, this is about 900 base pair square per second is the typical diffusion coefficient of a protein. It is a non-specific protein going along non-specific sites of DNA. So, this is the basically the answer. So, now let us convert this and calculate the viscous drag. So, viscous drag zeta is basically k b t by d. Now, what is k b t? 1 k b t is actually about 10 power 21 joule. For when t is equal to about 10 power 2 Kelvin, this is roughly 10 power 21 joule. And so, let me put an approximate notation here, because I am approximating k b t to 10 power 21 joule, because k b is 10 power minus 21 joule. K b is 6 something into 10 power minus 23 in units, in SI units. So, this is 10 power minus 21 joule divided by d, and d we said is basically in unit of centimeter square per second we know. So, we can write it in terms of even base pair square second. So, this is approximately 10 power minus 21 into 10 power minus 12 centimeter square per second into joule. So, this is basically 10 power minus 9 joule by centimeter square second. So, this is the, and you can convert this into meter. So, base pair square second and all that. So, but this is the viscous drag. This is the viscous drag that you have to you will calculate approximately. Okay. So, this is the answer to this question, but how do we can also calculate diffusion coefficient. So, we will see next question and see how to calculate diffusion coefficient. So, let us look at this question on calculating diffusion coefficient. So, this is our next question. Okay. So, imagine that you are cooking potato, adding salt and spices. This is something that you do every day, and assume that it takes about 1 hour for all the spice powder particle to diffuse into the potato pieces. Assuming that potato pieces have a radius of 2 centimeter, calculate the diffusion coefficient of spice powder particles inside the potato. Okay, this is some example which you can think, which basically to train to think, all of you to think that something that we see in everyday life can be thought of as a mathematical problem, and then you can apply this idea that we learned and learn something from day to day life, like something, all this is applicable in the things that we see in everyday life. So, something cooking potato. So, that is what we are thinking about here. So, let us think about it. So, you have a potato, and we said that the radius is about 2 centimeter, and you are putting spices, salt, etc. in to cook the potato. So, all the spice particles will diffuse and it will reach here. So, it has to travel a distance of this much and reach to the core. So, that everywhere is nicely salted and spice reaches everywhere, and it says that it takes about 1 hour for it to completely diffuse and reach here. Then what should be the diffusion coefficient? You have to know only this much, how long it really takes for it to diffuse, and if it takes about 1 hour, then we can estimate the diffusion coefficient based on this information. So, let us do this calculation. So, this is again based on this relation that the distance, like r square average, the average RMS distance is 2 dt in 1D. Let us do imagine one dimension thing first. So, it is 2 dt. So, now we do not know d, but we know t. So, t is 1 hour, which is basically 60 minutes, which is 3600 second. Now, what is r square average? The typical distance is 2 centimeter. So, square of the distance average has to be about 4 centimeter square. So, this is r square average, the average distance is about 4 centimeter square. So, from this we know t, we do not know d, but we know this. So, let us substitute 4 centimeter square. So, centimeter is converted into meter. So, 10 power minus 2 meter is equal to 2 into d into 3600 second. So, from this d is basically equal to, so let us go here. So, d is basically equal to 4 into 10 power minus 2 whole square divided by 2 into 3600. So, this is the answer. So, you can write 4 into 10 power minus 4. This is 3600 into 2, you can say 7.2 into 10 power 3. So, this is approximately 4 by 7.2 is about half. 10 power 3 into 10 power minus 4 is 10 power minus 7, and the units here is basically meter square per second. So, this is the diffusion coefficient of the spice particle if it takes 1 hour to diffusion reach the middle of the potato. So, this is also to give you some idea about some numbers. So, this is one question. Another question about diffusion, that something diffusion what we had discussed is what we will discuss in the next question. So, this is again a simple question. So, next question, let us this. Imagine a one dimensional tube through which a particular protein is diffusing. So, imagine a one dimensional tube through which at a given time the protein concentration is given by this. Calculate the current. What will the concentration change with time? You have to answer these two questions and do the same whatever we did for the above problem for if the C e of x is 10 power x square. So, the first question is calculate the current. So, we learned that the current J is basically d del C by del x, x cap. So, this is the minus sign. So, this is the definition of J. So, now let us look. We have C is equal to minus 10 x plus 100 del C by del x, we have to calculate from this. So, which is minus del by del x of minus 10 x. So, minus del C by del x, which is what we want, and there is a d here. So, I can multiply with d. So, d del C by del x minus 10 x plus 100. So, minus and minus becomes plus. So, this will lead to, this is equal to d into del by del x of 10 x plus del by minus del by del x of 100. This is 0 because derivative of a constant is 0, and this is basically just 10. So, this is d into 10. So, 10 d is the current. So, there is a current in the x direction which is basically 10 d. So, this is basically the current along the x direction. This we can think of by plotting this function. So, basically we are asked to use the function which is minus 10 x plus 100. If you plot this, the function will look something like this, minus 10 x plus 100. So, the slope is negative. So, that means the concentration here is less compared to the concentration here. This is C plus x. So, if the concentration is down here, it should just flow in this way. But will at any point will the concentration change with time? The answer we know physically is that it will not, because whatever comes in will flow out, because the flow is a constant everywhere. Flow is just a constant 10 d into 10. This is our J current or flow. So, it is just d is a constant, 10 is a constant, the flow is a constant flow everywhere. So, whatever comes in will go out. So, whatever the answer we get will be that the del C by del T will be 0. So, that is the next part of the question. Will the concentration change with time? So, that is the next part of the question. So, the answer to this question is that the change in concentration del C by del T is basically d del square C by del x square. So, in other words, we have to just do del by del x of the J we got. So, the J we got as 10 d, and derivative of 10 d is basically 0. So, del c by del t is 0, which implies that c is a constant. C will not change with time. So, the concentration, the answer to this question, will the concentration change with time? The answer is no. The concentration will not change with time, because J is a constant current, or del C by del T is 0. So, then therefore, C will be a constant. So, now the next question is, again you can see something here at the bottom. Do the same for C of x is equal to 10 x square. Calculate the current and calculate the change in concentration for 10 x square. So, let us do this. So, the current we saw is del C by del x, which is J x cap. So, then if you do this, minus d del by del x of C is basically 10 x square. So, this is basically derivative of 10 x square is 20 x. So, this is minus 20 d x x cap. So, this is the answer, and if you calculate the second derivative, del square C by del x square with d is one more derivative of this. So, the answer will be minus 20 d. So, and this is actually some non-zero value. So, therefore, so the del C by del t will be some number non-zero. So, this is in the second case, the answer is a non-zero current, and the concentration will change with time. Here the concentration will not change with time. Okay, so, we can think about this, you can do this in detail if you want. You should do this carefully. I just quickly showed you the answer. Now, what we should do is basically to calculate integral of a interesting function that we learnt called Gaussian function, or a normal distribution had this function called Gaussian function. So, how do we calculate the integral of this Gaussian function is one question that I want to discuss in tutorial. So, let us discuss this, because this has a lot of ramifications, a lot of times this has a lot of. So, what we want to calculate the integral of e power minus a x square. This is the Gaussian function. So, what we want to calculate is integral minus infinity to infinity e power minus a x square dx. This is the Gaussian function, and we even discussed the answer, but how do we get the answer? Whatever, that is the question. How do we do this? It's a, you have to do it in a, it's easy to do in a special way. So, I will discuss this, and the answer is used very much in many cases in probability and so on and so forth. So, let us do this carefully and learn how to do this. Okay, so, the answer we want. So, let's discuss this. So, what we want is basically I is dx e power minus a x square minus infinity to infinity. Now, x is the variable here. I could as well use y instead of x. I could also write this the same thing to write x is just a variable. I could use y, z or anything I want. So, let me use y. This also will give you the same answer. This and this both have the same answer, because I just change the variable. X is just a dummy variable, and I could change it to any variable I want. Instead of x, I could use z, y, k, whatever I want. And therefore, I am writing it as dy e power minus a y square. So, this now I multiply this two. So, that I get I square product of, which is basically minus infinity to infinity dx minus infinity to infinity dy e power minus a x square into e power minus a y square. This is what we have, and this is, so there is some reason for me to write like this. So, I can write this as e power a minus a into x square plus y square. So, this is nothing but, so I can write this part of it as I square is dx dy e power minus a into x square plus y square. So, this is basically a double integral. So, this is double integral dx dy e power minus a x square plus y square. Now, this integral is overall, it is the integral in a plane x and y, it is integral in a plane. So, anything in a plane can be either described by Cartesian coordinates x and y, or you can also use plane polar coordinates. That means, r and theta instead of x and y. So, if I use plane polar coordinates r and theta, what do I get is that, how do I do that? I can substitute x is equal to r cos theta and y is equal to r sin theta. So, e power minus x square plus y square times a will be e power minus a into x r square cos square theta plus r square sin square theta is just r square. So, it will be e power minus a r square. Then we have an integral which is dx and dy. So, how do we convert this into plane polar? This is the area element, this area under in Cartesian coordinate. The area under polar coordinate is basically r d theta dr. So, r d theta is basically, if you have a radius, r d theta is the area in this way, and d theta changes and r changes in this way. So, this is basically an area element in plane polar coordinate r d theta dr. So, dx dy will go to r d theta dr and x square plus y square will go to r square. So, this integral will essentially, we can rewrite. So, the integral we have now is basically integral minus infinity to infinity dx dy e power minus a r square, whereas dx dy we convert this into r d theta dr e power minus a r square. Now, think about it. So, now we have to decide what are the limits here. So, when it was x and y, the limits were minus infinity to infinity. What does it mean? It will go, x will go from all over here to all way minus infinity to plus infinity. Y will also go from minus infinity to plus infinity throughout this plane. So, this integral was throughout the plane. So, now in the plane polar coordinate, r is the radius and you cannot have negative radius. So, r integral will go only from 0 to infinity. So, you have 0 to infinity dr and theta is the angle, this will go from 0 to 2 pi. 0 to 2 pi theta and 0 to infinity r, and then have r e power minus a r square. So, if you substitute this became this, and we just rewrote everything and just put the right limit. So, instead of minus infinity to infinity, here r will go from 0 to infinity and theta will go from 0 to 2 pi. So, then this will complete any any for example, any circle or anything the function in 2D. So, these two integrals are equivalent. So, you can as well do this integral. Now, when we try to do this integral, let us try to do this integral carefully. So, now look at this. This part is actually independent of theta. So, only dr, r and e power minus a r square. So, this is independent of theta. Therefore, this theta integral can be just only this part. So, I can do the theta integral 0 to 2 pi d theta is just integral d theta is just theta, and if you apply the limit 0 to 2 pi, this becomes just 2 pi. So, this part of the integral is just 2 pi. So, let me write 2 pi. Then you have integral 0 to infinity dr r e power minus a r square. So, how do we do this now? How do we do the 0 to infinity dr r e power minus a r square? So, this can be done by taking r square as something. So, let us take r square is equal to t. So, then I take derivative both sides, 2 r dr is dt. I take derivative both sides. So, 2 r dr is dt, which implies that r dr is dt by 2. So, instead of the r dr here, I can substitute dt by 2, and instead of r square here, I can substitute t. So, if I do these substitutions, this become 2 pi integral 0 to infinity r dr is basically dt by 2 and e power minus r square is basically t square. Sorry, r square is t and there is an a, e square minus a t. So, there is dt here, dt by 2. So, this 2 and this 2 cancel. So, you have pi integral dt e power minus a t 0 to infinity. This is an easy integral to do. So, what we end up is basically pi into 0 to infinity e power minus a t dt. This is an easy integral that we all know, which is basically e power minus a t by a is the integral of this e power minus a t in the limit 0 to infinity, and you have pi here. Now, if we apply the limits to this, which is e power minus a t, if you apply this limits, what you get pi into e power minus a into infinity. So, e power minus a into infinity divided by a minus e power minus a into 0 by a. So, e power minus infinity anything is 0. So, this term is 0. So, this part basically 0, and what you have is just this part. So, e power 0 is 1. So, what we get is basically pi into this is 0 minus, and there is another minus sign, because e power minus a by minus a is there is a minus sign extra, because when you integrate c power minus a t by minus a is what the integral is, and therefore, a minus sign. So, 0 minus 1 by a. So, the answer is basically pi by a. So, I square, the square of the integral is pi by a. This implies that I is basically root of pi by a. So, this is a well known result. that the integral of a Gaussian, integral 0 to integral minus infinity to infinity e power minus a x square dx is root of pi by a. So, this is a well known simple result to understand, but it is a very useful result many times in statistics and many other contexts, the integral of a Gaussian function. So, this will come many occasions. So, once you know this, you can calculate many other interesting integrals like integral x e power minus a x square dx, integral x square e power minus a x square dx, and so on and so forth. So, this is if you multiply, if this is taken as a distribution and with a constant a, this will become x average and x square average. So, while we discussed x average and x square average, we discussed some part of it. This might also come again, but these integrals are very useful once we know that e power minus a x square integral is root of pi by a. So, let us quickly look at how to do this integral, which is x square e power minus a x square. So, what we want to do is that integral minus infinity to infinity x square minus e x square dx. Now, if you look at this carefully for a minute, as we said before, this can be written as minus del by del a of e power minus a x square is nothing but minus, this is minus x square e power minus a x square. So, this is x square e power minus a x square. Minus del by del a of e power minus a x square is this. So, then this is what we want here. So, instead of this I can write this. So, let me write this minus infinity to infinity minus del by del a of e power minus a x square dx. So, this has been rewritten in this particular fashion, and this is derivative with respect to a and integral is with respect to x. So, they are independent. So, I can exchange. So, that means, I can do first the integral and then the derivative, and the answer to this integral we know, which is root of pi by a. So, we have to just find the derivative of root of pi by a. So, what we finally need to do is to just to find the derivative of minus del by del a of root of pi by a. This is all we have to do to get this particular integral. So, then we get the answer. So, this is basically root of pi into minus del by del a into a power minus half. So, it's basically minus half with a minus sign here, plus half root pi into this half a power minus 3 by 2. So, this could be the answer. This is the answer. This is plus sign here. So, it's basically root pi by 2 into a power minus 3 by 2. So, this is basically x square e power minus a x square integral dx. So, this is minus infinity to infinity. So, all this is applicable. We just wrote the result of the Gaussian integral as root of pi by a, and you get this particular answer. So, with this many questions that we discussed, a couple of integrals and some vector notation and diffusion and so on, we covered some quick important points about some tutorials, and again I will give you a set of problems as tutorials in the write up. So, we will with this tutorial we will stop today's discussion, and we will continue the rest of it, the other lectures in the next class. Bye.